All right, we are recording. I want to welcome you all to the database or outside the mainstream. We have this as a 24-hour, 7 days a week tool. So those who want to use this, just let us know. It is sponsored by the MPA, Natural Philosophy of Science, and the Thunderbolts Group, the Electric Universe people. We thank them very much for paying the, oh my goodness, I think it's $500 or $600 or even more per year to have this forum. Video conferencing, as much as it seems easy and free, is not so much. So it does cost, and the moment you give about between 25 and 100, the price goes up, and then after 100 even goes way through the roof. So we do appreciate anybody's donations too. You can donate through the World Science Database right at the top. Click on that, and any donations accepted. That helps keep this going, this forum going, which is a great forum. It's a lot cheaper to have this than it is to fly somewhere. So we welcome everybody from around the world. I know we've got them from everywhere. And today we have André Assis from Brazil. There are now, I think, 27 Brazilians in our World Science Database who are doing, a lot of them doing really great work. I know André Assis is a professor at the university. He's even appeared on television, sort of like the Tonight Show. You can see that, I think, in his profile. We have put that online for you. And so he's out there spreading the word as much as he can. He has some books. Check out his books. They're really great reading. I believe he said he'll be part of the NPA 18 this year, which is happening in Maryland in July of 2011. We hope to see everybody there. I know a lot of Electric Universe people are going to be there this year. So we're expecting, we're hoping well over 200 people at the conference. And he's been a member of the NPA for some time now, doing some really great work. And without further ado, I'll let him take over here. And André, why don't you give a little bit of background for those who don't know you? It would be good to tell us a little bit about yourself, because we are getting new people here who maybe people have heard you and others who haven't, and give us a little background on how you got into this. I know also you're in the university and have some students, and that's also great. And André told me this was to be about an hour, so I'll give you an idea, and then afterwards we'll have plenty of time to discuss and talk, which is always great. So get your webcams and microphones ready, and thank you very much, André. Bem-vindo, obrigado, e pode falar.
Thank you very much, David, for the invitation to be here today with all of you, and also Greg Falk. It's a great pleasure for me to be here. This is the second time I'm talking at a video conference at Natural Philosophy Alliance. I'm Brazilian. I did the study at the University of Campinas, and where I did my PhD in plasma physics. And during my postdoc position in England, I did begin to work with Weber's Electrodynamics, which is the subject of our talk today. At the University of Campinas, I also supervise graduate students, PhDs, and others postdocs in Weber's Electrodynamics, in Relational Mechanics, and other topics. For those of you who have an interest in our homepage, which is presented in this first slide, all of our papers, they are available there in PDF format. So the plan of the talk today will be for me to present an overview of Weber's Electrodynamics in the first half, general overview, and then we go to a specific comparison between Weber's force and Lorentz force. So before we we present the Weber's electrodynamics, I just, in this slide here, I present classical electrodynamics, which is based on Maxwell's equations, 1861 to 64. There are 4 field equations. The first one is the law of Gauss, relating the electric field E with the volume charge density rho, which is essentially a field formulation of Coulomb's force. The second equation is the similar equation for the magnetic field, saying that the divergence of the magnetic field is 0, meaning that there are no magnetic monopoles. The third equation is Faraday's law of induction. The rotational of the electric field is minus the temporal variation of the magnetic field. This is in vector notation. And the fourth equation is usually called Ampere's law, with the displacement current introduced by Maxwell. As a matter of fact, Ampere never wrote anything like that because he didn't work with magnetic fields. Later on we will see what Ampere did really do. In any event, there is this magnetic or Ampere's circuital law, and these 4 equations connect the fields, but we also need to an expression for how the fields act upon a test charge. This is supplied by Lorentz Force law, 1895. F equals QE plus QV cross V. This V is the velocity of the charge. Lorentz originally believed that it should be the velocity of the charge relative to the ether. But since Einstein's theory of relativity, 1905, the meaning of this velocity has changed. Nowadays, we say it is the velocity of the test charge relative to a frame of reference. It is a very strange situation. So this is classical electrodynamics. But what we will discuss today is another formulation which was developed by Wilhelm Weber. He was a contemporary of Maxwell. He was born in 1804, before Maxwell, and died in 1891, after Maxwell. He was born in Wittenberg, and his main position at the university was in Göttingen. He was hired as a professor of physics, working in collaboration with Gauss. He worked there from 1831 to 43. Then he lost his position at the university for political reasons with the government of Hanover at the time. Weber was one of the Göttingen 7 professors. The others were the brothers Grimm of the fairy tales and other. And so during 6 years, he did move to Leipzig University. And it was during his Leipzig time that he did develop his electrodynamics, which we will be discussing today. Later on, he did come back to Göttingen in 1849 and was at the head of the Physics Institute and also of the observatory. And he stayed there until his death. So let us see what were the main steps which he did follow in order to arrive at his force law. This he did obtain in 1846. His original paper has already been totally translated to English, and you can find it in our homepage in PDF as well. So he knew Coulomb's force, 1785, which is essentially analogous to Newton's law of gravitation. The force is proportional to the product of the two charges, follows as 1 over r squared, and it is a central force. He also knew Ampere's force between current elements, 1822, which is also similar to Newton's law, proportional to the product of the two currents, I1, I2, is a central force and follows as 1 over r squared. But it is more complex expression because it depends on three angles, alpha, beta, and gamma, which are the angles of each current element with the straight line connecting the two current elements, and also the angle between the two current elements. And here, Weber also knew Faraday's law of induction, stating that the electromotive force, EMF, is proportional to the time variation of the current in the primary circuit. So that if you change the current in the primary circuit, you induces a current in the secondary circuit. So Weber wanted to unify these three components of electromagnetic interaction, like Maxwell, but Weber did not work with the field concepts. Weber did work with the force concept. So he wanted, for instance, he wanted to derive Ampere's force from a generalized expression of Coulomb's law. So his idea was to suppose that current is charge in motion. Essentially, a current element, IDL, will be equivalent to charge times velocity, QV. So if he were to derive Ampere's force from a generalized Coulomb's law, there is no velocity component in Coulomb's law. So he did need to introduce in the bottom equation in this slide the middle component, which is a constant times V1, V2, the velocity of the two interacting charges. So the middle term he introduced in order to derive Ampere's force between current elements. And if current is charge in motion, Faraday's law of induction means that when you change the current, you are accelerating the charge in the primary circuit. And this induces a force upon the charge in the secondary circuit. So if current is charge in motion, di by dt is proportional to acceleration. So Weber introduced in the bottom equation the third term, which depends on the relative acceleration between the two charges. So essentially, his idea was to unify the three aspects of Coulomb, Ampere, and Faraday in a single force law. So his final expression is presented in this slide, but now we are presenting Weber's force in the international system of units and utilizing vector notation, which was not presented in this way by Weber. So it is essentially Coulomb's law, Q1, Q2 over R squared. It is a central force, but it also depends on R dot, which is the relative radial velocity between the two interacting charges. And it also depends on R2 dots, which is the second time derivative of the distance between the interacting charges. So the middle component will lead to Ampere's force, and the third component will lead to Faraday's law of induction. Notice that the third component follows as 1 over R, as is well known in electromagnetism. And Weber did introduce a constant in his force law, which is presented here as C. In 1846, he didn't know the value of this constant, which is essentially purely electromagnetic constant, which is the ratio of electromagnetic and electrostatic units of charge. And Weber was the first to measure this constant. That was in 10 years later, 1856 together with Koch, and they found that C is 3 times 10 to 8 meters per second, essentially light velocity in vacuum. So this was one of the first indications of a connection between electromagnetism and optics. So what we will present here briefly is an overview of Weber's electrodynamics. To those of you who have an interest, we have published a book in 1994 in Holland by Kluver on Weber's electrodynamics. We will present just some few topics here. The details are in this book. So the main properties of Weber's force. In the static case, when there is no relative motion between the interacting charges, dr by dt, and the second time derivative of the distance goes to 0, we return to the laws of Coulomb and Gauss. So electrostatics is built into Weber's force. It complies with action and reaction. This means conservation of linear momentum of the interacting particles. Moreover, the force is along the straight line connecting the particles, which means conservation of angular momentum as well. Weber showed that his force law can be derived from a velocity-dependent potential energy, which is U, Q1, Q2 over R, which is the Coulomb potential energy, but it depends also on R dot square. So this was the first example in physics of a potential energy which depends not only on the distance between the particles, but also upon the relative velocities. So he showed that his force law complies with conservation of energy. The sum of the kinetic plus the potential energy of a group of interacting particles is constant in time. So this is a very important result. Moreover, Faraday's law of induction can be derived from Weber's force. We will not show the details here. For those of you who have an interest, you can read Maxwell's book, A Treatise on Electricity and Magnetism. The last chapter of Maxwell's book is devoted to Weber's electrodynamics. And so there, Maxwell shows that Faraday's law of induction can be derived from Weber's force. Also, Faraday's circuital law can be derived from Weber's force, because Weber knew Ampere's law, and he built his force law in order to derive Ampere's law. But what attracted me to work with Weber's law in the first place was that it is a central force, complies with action and reaction, and that it is completely relational. What I mean by that is that the Weber's force depends only on the distance, r, between the charge, dr by dt, and the second time derivative of the distance between the interacting charges. So it has the same value to all observers and to all systems of reference. It depends only on magnitudes intrinsic to the system of interacting charges. It depends only on the relation between the bodies. This is different from Lorentz Force law, in which the velocity which appears there is not the velocity of the charge relative to other charges, but the velocity of the charge relative to the frame of reference, which is very strange to me. So when I found Weber's force law, it did appeal to me, to my physical intuition. And so I decided to work with it. And I have been working with Weber's law for 20 years now. So, in particular, the international system of units. I1, I2 over R squared, and it is a central component, depending also on the three angles, as I said. But this Ampere's force was called by Maxwell the cardinal formula of electrodynamics, the most important formula of electrodynamics. But nowadays we don't find it in the textbooks. Nowadays we only find the bottom equation, which is Grassmann's force law. And from Lorentz, we derive Grassmann's force. Instead of QV cross B, we have IDL cross B, where the B is the magnetic field of Biot-Savart. When we open the double cross products, we end up with the bottom equation, which is similar to Ampere's, but it's not equal. They are numerically different, and they do not point along the same directions. In order to illustrate the distinction between Ampere and Grassmann, we can see in the top figure, the top situation in this slide, we have two current elements which are orthogonal to one another. If we calculate the force between these two current elements with Ampere's law, it gives 0. One does not act upon two and vice versa. But with Grassmann or Lorentz force, the second current element exerts a force upon the first one pointing upwards. But the first current element does not act back on the second. So Grassmann's force does not comply with action and reaction. In the middle situation, we have now two current elements which are parallel and aligned with one another. In this case, Ampere's law predicts a repulsion between these two current elements. And Grassmann's law, on the other hand, predicts no interaction. There should be 0 force. So they are very different. But there is a sad point that when we integrate the force of a closed circuit 2 acting upon a current element 1 of another circuit, both expressions, they agree with one another, and they can be written in the usual way, IDL cross another expression between parentheses, which in the textbooks is called magnetic field of the second circuit, acting upon the first current element. So, but this equivalence is only for closed circuits. We will not go into more details here. For those of you who have an interest, we have a whole book called Inductance and Force Calculations in Electrical Circuits, published in 2001, devoted wholly to a comparison between Ampere and Grassmann. And we show that they are the net force on a current element will be the same for both expressions whenever we have closed circuits, so that we cannot distinguish them, unfortunately. So, a last topic related to Weber's electrodynamics is that in 1857, Weber and his student Kirchhoff, they did show the propagation of electromagnetic signals according to Weber's law. So they applied a generalized Ohm's law, which is the first equation here, taking into account the time variation of the current or of the vector potential. And the second equation is the equation of the conservation of charges. With these two equations and Weber's electrodynamics, they did derive the telegraphy equation for a signal propagating along the wire. This is the third equation in this slide. At the left side, we have the wave equation. At the right side, we have a first derivative, which is proportional to the resistance of the medium. The Greek letter C or chi here can mean the current, the surface charge, the scalar potential or the vector potential. If we have a medium with negligible resistance, Weber and Kirchhoff did show that the signal would propagate at light velocity if the right-hand side of the last equation goes to 0. And this was shown by Weber and Kirchhoff before Maxwell introduced the displacement current and before Maxwell obtained the wave equation. When Maxwell introduced the displacement current, he did borrow the constant c from Weber's force. He also knew the numerical value of this constant, which Weber had measured for the first time in physics in 1855 and 56. And Maxwell also knew this work by Kirchhoff, showing the telegraphy and the wave equation obtained from Weber's electrodynamics. This is not presented in the textbooks, but this is a historical fact. Everything was known about propagation of signals with Weber's electrodynamics before Maxwell. So, up to now, this is the short overview I want to present about Weber's electrodynamics. So, with Ampere and Glassman, we cannot distinguish the two formulations because we always had closed circuits with steady currents. And also in this situation of propagation of electromagnetic signals, we have equivalent equations and results from classical electromagnetism and from Weber's electrodynamics. What I will present in the second half of my talk is clear situations where there are different predictions between Weber and Weber's electrodynamics and classical electrodynamics. So my main subject in this talk is here, Weber versus Lorentz. So we will be comparing Weber's force, which is the top equation here, Coulomb, plus the velocity term, plus the acceleration term between the interacting charges, and Lorentz force. So even from the form of these two equations, we can see that they are different paradigms. The Lorentz force is based on field concepts, and Weber's is not. Moreover, the velocity v, which appears in Lorentz force, is the velocity of the test charge relative to the frame of reference. And in Weber, this is not the case. In Weber, there is only relative velocities and relative accelerations between the interacting charges. So let us see the clearest, the simplest situation in which we can compare these two formulations. So in this slide here, I am just for comparison. You don't need to take notes of all the mathematical details here, but I presented here Weber's force of a charge 2 acting upon charge 1. So Weber's force depends on both velocities, v1 and v2, and depends also on both accelerations, a1, a2. a1 is acceleration of the test charge, a2 is acceleration of the source charge. Lorentz force, on the other hand, depends on v1, v2, but it depends only on a2. That is Weber's Lorentz force, if we express it in the Linear-Wishart formulation. It depends only on the acceleration of the source charge, but it does not depend upon the acceleration of the test charge. There is no dependence in Lorentz force on A1. And this dependence appears in Weber's force. So we will show how can we distinguish these two formulations, in which experiment could we perform to distinguish them. So The slide which I'm presenting here is the most important slide of this whole presentation. Here we are calculating the force of a uniformly charged insulating spherical shell acting upon an internal accelerated test body. So the test body is small q, is inside the spherical shell, and the spherical shell has a net charge, capital Q, uniformly distributed over the sphere. And the sphere is supposed to be an insulating sphere. And we try to accelerate the test charge. For instance, if it is a pith ball, I can accelerate it with my hand, or I can connect it to an oscillating spring and so on. And we want to know if there will be any force exerted by the shell upon the internal accelerated charge. According to Lorentz Force, the shell does not exert any force on the internal charge because there is no electric field inside by Gauss' law, and the shell is stationary and it's not spinning, so there is no magnetic field as well. So Lorentz Force, it does not matter if the surrounding shell is charged or not, because there is no force exerted by the shell upon the internal body. With Weber's force, on the other hand, the force exerted by the shell upon the test body is not zero. It will be proportional to the product of the two charges, test body and shell, and will be inversely proportional to the radius of the shell, spherical shell. And it will be proportional to the acceleration of the test body relative to the shell. These calculations have been presented in a paper which we published in 1993 in the Journal of the Physical Society of Japan. It is called Changing the Inertial Mass of a Charged Particle. For those of you who are interested in Weber's electrodynamics, try to repeat this calculation. This is the most important calculation of all. And you can do it very easily in the simplest situation in which the test body is passing exactly through the center of the shell and accelerated along the z-axis. In this case, the integration is very simple, and you will see that Lorentz gives zero, but Weber does not give a zero result. Gives this result presented here. Mu naught Q1, charge of the shell, divided by 12 pi r times the acceleration. Just try to repeat this calculation, only this, and you will understand the difference between the two formulations. So then how can we make an experiment? So let us see how will be the equation of motion for an electron accelerated inside a uniformly charged spherical shell. According to Lorentz, it will be simply Newton's second law, at least for low velocities. F equals ma, where F here will be the force exerted by my hand, by a spring, by a magnet upon the test charge. With Weber's electrodynamics, on the other hand, beyond the force exerted by the spring, by my hand, by the magnet upon the electron, there will be also a force exerted by the shell upon the accelerated test charge. So this is a second term in the left-hand side of the second equation here. We can pass the second term to the right-hand side, and then we end up with a similar to Newton's second law of motion. But now the test electron will behave as if, according to Weber's electrodynamics, the electron should behave as if it had an effective inertial mass depending upon the surrounding charges. And you can write this Weberian mass as QV over 3c squared, where V is the potential of the shell, supposing the potential to be zero at infinity. So for you to have an order of magnitude, if we can double the effective mass of an electron, if it is accelerated inside the shell charged to a potential of 1.5 million volts, 10 to the 6th power volts. So we can detect these in the laboratory. And it has nothing to do with relativity, because you can do the experiment with low velocity electrons. If the shell were spinning, then Lorentz force would predict a force upon the internal body. The electric field inside the uniformly charged shell spinning at a constant angular velocity is still zero, but there is a uniform magnetic field inside the shell. Outside it will be a dipole field, but inside it will be uniform. So Lorentz force will predict a force given by this equation here. The analogous expression according to Weber's electrodynamics is the bottom equation in this slide, which has three components. The first one depends upon the acceleration of the test charge. The second one is analogous to the centrifugal force, which has no similar in Lorentz component, and it can be called an electrical centrifugal force. And the last component of Weber's formulation is similar to Coriolis force of mechanics. And it is this Weberian Coriolis force which is similar to the magnetic force of Lorentz. So we derive the magnetic components with Weber's electrodynamics, but there are two extra components. So from now on, I will discuss the situations in which the spherical shell is at rest. So the idea is to see situations in which we can see these results. So what are the evidences for a component of the force depending upon the acceleration of the test body? I will begin with gravitation. In 1925, Schrödinger derived the precession of the perihelion of the planets utilizing a Weber's potential energy for gravitation. This was his last paper before his development of the quantum mechanics. In this paper, he showed that there will be a precession of the perihelion of the planets according to Weber's law applied to gravitation, which is algebraically and numerically equal to the prediction of general relativity, but with a completely different interpretation. And in this paper, Schrödinger said the following: the presence of the sun has, in addition to the gravitational attraction, also the effect that the planet has a somewhat greater inertial mass radially than tangentially. So, according to Weber's law, the component of the acceleration depends upon the surrounding charges. In the spherical example, which we discussed before, the effective inertial mass will be isotropic. The acceleration in any direction will be affected. But in the case discussed by Schrödinger, the radial direction connecting the sun and the planet will increase the effective mass of the planet, but there will be no increase in the tangential direction. And it will be this distinction which causes the precession of the perihelion of the planets according to Schrödinger and Weber's law for gravitation. There are many other examples in gravitation, essentially in relational mechanics, which is based upon a Weber force law for gravitation. It leads to a mathematical implementation of Mach's principle. The inertial mass is due to, according to relational mechanics, the inertial mass is due to a gravitational interaction between the test body and the set of the distant galaxies. In relational mechanics, it is derived the proportionality between inertial and gravitational masses. We don't need to postulate this result. We derive this result numerically from the equations. Moreover, we derive that all inertial forces minus ma, the centrifugal force and the Coriolis force of mechanics, they are real interactions. They are not seen as fictitious forces any longer. According to relational mechanics, these inertial forces, they are due to a relative acceleration between the test body and the set of distant galaxies. For instance, in Newton's bucket experiment, it does not matter if you rotate the bucket with water relative to the galaxies or if you let the bucket stationary and rotate the universe in the opposite direction. In both situations, you will have the curvature of the water. I will not go into the details here because we presented a talk last year on relational mechanics, but you can see this book that we did published in '99 in Canada with Ampere, the publisher. Roy Keyes is the editor. So in this book, we can see all the details of this implementation. But now I will go back to electrodynamics. There has been recently a paper published by Mikhailov. He published an experiment showing an effective inertial mass of test electrons depending upon the surrounding charges. He made this experiment in order to test Weber's electrodynamics. His paper is called "The Action of an Electrostatic Potential on the Electron Mass." It was published in the Annales de la Fondation Louis de Broglie in France in 1999. Mikhailov utilized a neon glow lamp RC oscillator placed inside a glass sphere of radius 5 centimeters, having indium gallium plating, which he did charge the sphere up to 2 kilovolts. And he did measure the oscillation frequency of the lamp. And he observed that this oscillation frequency depended upon the potential of the shell according to Weber's law. This was the first experiment, to my knowledge, ever proposed in order to test this prediction of crucial prediction of Weber's law. It's completely different from the prediction of Lorentz Force. Junginger and Popovic from Canada did not confirm these results. They published a paper in the Canadian Journal of Physics 2004, which is called "An Experimental Investigation of the Influence of an Electrostatic Potential on the Electron Mass as predicted by Weber's force law. However, it's not a precise repetition of Mikhailov experiments. In particular, instead of a coated glass shell, which may have worked as a charged insulator in Mikhailov's experiment, Junginger and Popovic utilized a conductive enclosure tin foil, cubic foil, with dimensions 40 by 40 by 40 centimeters. So Mikhailov had a sphere. Popovic and Junginger had a cubic enclosure. But the main difference is that Junginger and Popovic utilized a conducting enclosure, while Mikhailov utilized a glass sphere, which may have worked as an insulator. The relevance of this distinction is that for a conducting charged sphere, for instance, the electrostatic force will be zero upon the test charge only when it is at the center of the shell. If you move the test charge away from the center, but still inside the spherical shell, if the spherical shell is conducting, there will appear image charges upon the surrounding shell, and they will act upon the test charge. So the force will no longer be zero when the test charge is outside the center. This will not happen for an insulating sphere, because in this case, the charge upon the sphere do not move, and the force upon the test internal charge will be zero, no matter its position inside the shell. So this is a very relevant distinction. Mikhailov did publish two other experiments confirming his earlier results. One was published in 2001, and he had a different setting. In this case, it was the frequency of a Barkhausen-Kurz generator, which is a flux of mobile electrons, which he did observe that this frequency of this generator did depend upon the voltage of the surrounding glass sphere. 2 years later, in 2003, he measured the oscillation frequency of a neon glow lamp inside two spherical concentric shells. Once more, glass shells. The internal shell was connected to the circuit of the generator and could be connected either to the earth, the grounding, or to a source of high voltage by a switch. The external shell was connected to a source of high voltage, which could be changed at will. Mikhailov observed that the oscillation frequency of the lamp depended upon the voltage of the shell, with exactly according to the prediction based on Weber's electrodynamics. To my knowledge, he did not make other experiments, Mikhailov, on these three. So, these are very important experiments, and I wish to point out this distinction between these results. There is another very important evidence that there is a component of the force law depending upon the acceleration of the test charge. This is a paper which we published in the European Journal of Physics, 1997. The title of the paper is Circuit Theory in Weber Electrodynamics. In this paper, we show that the self-inductance of a circuit may be interpreted as being due to an effective inertial mass of the conduction electrons, as being due to the acceleration of the conduction electrons in relation to the positive lattice of the metal. If you wish, we can go to the details later on. I will just skip 3 slides here because they are more mathematical and they will take some minutes to explain. But the essence of this paper is that we show that when you try to accelerate the conduction electron relative to the lattice, according to Weber's electrodynamics, exerts a force upon the conduction electrons, which depends upon the acceleration of these electrons. And this force will be equivalent to an effective inertial mass of the electrons 10 orders of magnitude greater than the free mass of the electrons. And this 10 orders greater inertial mass will be exactly responsible for the self-inductance of the circuit. Moreover, it will depend on the geometry of the circuit and on the direction in which we try to accelerate the electrons in the circuit, axially, for instance, or tangentially, or along the poloidal direction. The barrier inertial mass will change from geometry to geometry, and this is known to happen with the self-inductance of the circuit. So later on we can discuss these topics, but now I want to present to you my last topic, which was the subject of my research in Germany at Hamburg University last year, together with Wiederkehr. Wiederkehr wrote the main biography of Weber, which was published in 1967. And this was my second time I did work with him in Germany. And this time, last year, we did make research on Weber's planetary model of the atom, which Weber did develop between essentially 1871 and 1880s. These papers by Weber have also already been completely translated to English. The paper from 1871 appears in the Philosophical Transactions in English in 1872, and his paper on the planetary model of the atom can be found in English in our homepage in PDF format. So, what Weber did study in this case? It was Weber wanted to study the equation of motion of 2 interacting charges, which were interacting with one another according to his force law. So, F equals ma, Newton's second law of motion. And the force now will be Weber's force, which depends on the velocity and acceleration, the second equation in this slide. For low velocities of the test bodies, we can neglect or disregard r dot square over c square because that will be negligible, but there will be the acceleration dependent component of Weber's force, which we are calling here MW, Weberian mass. These will, in many situations, will not be negligible. As Schrödinger has shown, this will lead to a precession of the perihelion, not only of the planets, but also in Weber's planetary atom. The electron in orbit should precess, It will not be a closed ellipsis, it will precess. But when we pass this Weberian nest to the right-hand side, we will end up essentially with charge times the electric field equals to a effective mass times the acceleration. And this effective mass will be the free mass of the tested body, m, minus the Weberian mass, Q1, Q2 over R. So this Weberian mass depends upon the sign of the two interacting charges and depends also upon the distance. When the distance between the interacting charges is very small, the magnitude of this Weberian mass can be very huge, can be large, can be greater than the magnitude of a free electron, for instance. So, if we have, for instance, two positrons with a mass of 9 times 10 to minus 31 kilograms and a charge of 1.6 times 10 to minus 19 coulombs. This was not known by Weber. But if we apply these numbers in this two-body situation, these two positrons, when they are very close to one another, they are moving relative to one another at distance smaller than what Weber called the critical distance, which in this case will be 10 to minus 15 meters. The two positrons, they will behave as if each one of them had negative inertial mass. So instead of repelling one another due to charge of the same sign, they will attract one another. So also Weber did not know about the existence of the electrons. He could predict these effects, and he proposed a planetary model of the atoms with negative charges orbiting in elliptical orbits, which would in general precess around a positive nucleus, and the charge of the nucleus would be held together by these Weberian interaction. So the nuclei would be stable due only to electrodynamic forces. So this was an amazing prediction. And when we put the numbers for the mass and charge of the electrons, and we finish obtaining a distance, a critical distance, that would be essentially the size of the nuclei of 10 to minus 15 meters, which is known to be the typical size of the nuclei of the atoms. It cannot be a coincidence. So this Weberian planetary model is totally unknown today. But it was published before the discovery of the electron by Thomson in 1897. It was published before the works of Rutherford and Bohr in 1911 and 1913. And it has a unique properties, as you can see in the second figure here. The electrons are orbiting around the nucleus, and the nucleus is held together by Weber's force. We don't need nuclear forces for the stability of the nuclei. The nuclei will be held together by Weber's electrodynamic force. This is an amazing, the only model known to me which has this property of the stability of the nuclei due only to electrodynamic forces. Weber even predicted that the we could have like radiation splitting of the nuclei depending upon the magnitude of the forces and so on. So, in conclusion, what can we say? That Weber's force is completely relational, that is, depending upon the relative velocities and relative accelerations between the interacting bodies. This is not the case with Lorentz Force law. Weber's law conserves energy, linear momentum, and angular momentum. Weber's law is compatible with the laws of Gauss, Ampere, and Faraday. That is, Weber's force, we have the whole of electrostatics, Coulomb's law, the whole electrodynamics of Ampere, interaction between magnets and current carrying circuits, and the whole of induction. Moreover, Weber's electrodynamics, or Weber's law in general, leads to the propagation of electromagnetic signals at light velocity. And Weber showed this before Maxwell. Weber and Kirchhoff, they did publish these results before Maxwell. And as regards the effective mass of a force depending upon the acceleration of the test body, there are many indications of a component in the force law depending upon the acceleration of the test body. One, in gravitation, we have the precession of the perihelion as shown by Schrödinger. We have Mach's principle, that the inertial mass is due to interaction with gravitation. The proportionality between inertial and gravitational masses. In relational mechanics, which is based on Weber's law applied to gravitation, we can derive Newton's second law of motion, F equals ma. We don't need to begin with an equation of motion. We begin only with Weber's force law. And we derive F equals ma exactly utilizing the acceleration component of Weber's law, which depends upon the acceleration of the test body. Moreover, we derive mathematically the proportionality between inertial and gravitational masses. And in electromagnetism, we have nuclear forces between quotation marks, that is, we can derive the stability of the nuclei utilizing Weber's force as Weber predicted in his planetary model of the atom. We don't need nuclear force, only electrodynamic forces to explain stability of the nuclei. We have these recent experiments by Mikhailov, which still need to be verified by others, but we do have the self-inductance of every circuit, which is very well known and which can be derived mathematically from a acceleration dependent force depending upon the acceleration of the test body. So these are very strong indications that this component is real. And to those of you who are experimentalists, I suggest to you to try not only to repeat Mikhailov's experiments, but other experiments, because we can do these with, we don't need to go to million volts. To million volts, we will have an effect of 100%, but with 100,000 volts, we will have a 10% effect, which is a huge effect. For 10 kilovolts, we will have 1% effect. We are huge effects. We don't need to go to high velocities. And to those of you who are theoreticians try to look at phenomena in solid-state physics, in nano physics, and try to find effects which indicate this property of Weber's law, or which are already known, but which can be seen from this paradigm, from this point of view. So thank all of you for your attention. Once more, Dave Hildster and Greg Falk for this invitation. And now I would like to discuss with all of you. Thank you very much.
Okay. Can you hear me, Andre? Oops, he's gone away. All right, I guess he's going to go get a glass of water or taking a break. We do have microphones available for anybody who wants them, microphones and video cameras. And also questions, if you want to type in your questions. I will put them in queue, so if you don't have a video camera or microphone, we can relay the question to Andre. Andre, Mikhailov's work, I noticed we don't have his work in our database. I think that would be, you say you have some of his papers. I searched on the internet and the links that I found weren't working. I guess they were from French website, but they seem not to be there. That's one of the things we could do, I think, is to create a profile for him in the database and get some of his papers. Is that something we can do with you?
Yes, no problems, because his papers, they are available in PDF format from the homepage of the Annales de la Fondation Louis de Broglie.
Okay, maybe what you can do is maybe send me some links, and we can create a profile in the database. That would be a good start. That way, if you're looking to have people wanting to look at his experiments, that would be a really great start. We can. Greg Volk said he can take care of it. That's fine. Okay, I do have. Again, we have. Video. We have 2 other video feeds or microphone. You don't have to have a video. You can have a microphone if you want to. One of the questions I see here is, or comments was Maxwell familiar with Weber's work?
Yes, he was very familiar with Weber's work. If we look at the index of Maxwell's treatise on electricity and magnetism, the 2 people he quotes the most are Weber and Faraday. So he knew quite well the works of Weber. And the last chapter of Maxwell's treatise, the whole book, the last chapter, is totally devoted to Weber's electrodynamics. All of you who did should give a look.
No, we don't. We don't have Ampere either. And Ampere, believe it or not, his original work has never been translated into English.
It seems like what we need to do too is one of the things I know Greg Volk is here. Greg, it seems to me that we should probably put Weber
his
in our
work, which is extremely significant and has the force laws
I think often, some of these bigger people like Maxwell, of course,
that really needs to be emphasized. And there's a lot of people working on Ampere's force laws and
historical people. What do you think?
Making connections that, as Maxwell himself said, was the most important equation in physics. So, and yet we don't even have it translated into English. It's a crime. So Weber and Ampere are 2 19th century heroes that we need to be emphasizing for sure. I have some questions, and first of all, I'm so happy that you're here, and I'm especially happy that you've managed to attract some of my heroes. Dr. Phipps is here, David Roscoe is here, Neil Greneau, I believe, is still here. These are people who have obviously followed your work and are kind of part of the people working in the relational view And as I am, I regard relational physics as the key to getting out of this Einsteinian mess that we have. And these are the people whose work I think is most significant. Another one is we'll be speaking soon is Christoph.
We do have a very long delay, just so everybody knows, about 20 seconds.
And I just like to call attention to the work of those people, because this is, in my opinion, this is the work that's going to change physics. Anyway, so I'll get off my soapbox. I have some particular questions. I would like, if you could, maybe you could email it later. If you could get it now, that'd be great. The actual reference to Weber's paper, you mentioned that predicting a positive nucleus and a negative shell. I was not aware of this until just now, and I'm very interested in that paper. So if you don't have it now, you can maybe send it to me later. Okay. My second question is the name of your German colleague. You didn't mention his name, but it seems to me that we ought to get him in the database as well. I mean, if he's working on this stuff. Go ahead. I'll shut up. Excellent. That doesn't help me. That's excellent. Thank you. That needs to be publicized. That's important work that really needs to be known.
Can I make a few comments?
If I may, can I just ask one more question before you start on that, and then I'll go away?
Yeah, we have a delay.
My question is, John Johnson, I don't know if you're familiar with his work, but he's a relational, working on relational ideas, and he's very much.
Again, we have a very long delay, so that's why there's.
He has a question. Recently wrote a paper. I don't know if you've seen it or not.
Just
in some of your work, you're claiming that in a closed circuit, there's no distinction between the Lorentz and the Ampere force, and he says that there is, even in a closed circuit. I just wondered if you know what this work is, and if you have any comments on that. It's sort of loosely related to what you're talking about today.
He has an excellent biography of Weber, which I recommend to all of you, and many papers devoted to Wilhelm Weber and to his electrodynamics. Greg, you mentioned about translation of Ampere's work. Last year, PhD student of mine, he finished a complete Portuguese translation of Ampere's book. And we are planning to also an English translation of, yes, but we...
Oh, that helps me, I'm fine. Great, thank you.
Of the book as well. So it should... okay. And maybe I could also try to answer some questions which I can see here in the chat. So, as regards your question, Greg, the paper by Weber with the planetary No. Oh, yes. Okay. This is a long controversy between Ampere and Grassman's force laws. So I will not go into the details here, but I do have many papers, and this book on Ampere versus Glassman. And then there we show that in all situations of closed circuit, they will give equivalent answers, unfortunately. Another point, the paper in which Weber has this planetary model of the atom with the positive nuclei and negative electrons orbiting around it, and in which the nuclei is stable by electrodynamic forces. It has already been totally translated to English, and you can find it in my homepage in PDF. You can download it from my PDF. I saw here a question by Mike Studenki. Is it possible to make m equals the Weberian mass and cancel inertial mass electrically? My answer is yes, that is possible. For instance, in the example I gave of a test electron, a freely moving electron inside a charged spherical shell, if the shell is positive, 1.5 million volts, the electron will double its inertial mass. But if the shell is 1.5 million volts negative, then the effective inertial mass of the electron will go to zero. So it should increase its velocity and acceleration very easily. Obviously, the velocity should not explode, go to infinity. For high velocities, for velocities close to light velocity, we will need some corrections. But for low velocities, it is possible to have particles with negligible effective inertial masses, like massless particles.
Okay, we have another question from Neil Greneau. I am wondering if Andre has any understanding of why a charged insulator has a different effect to a charged sphere on an internal charged particle.
Hi Neil, good to see you there today. Great honor for me. Thanks my best regards to Peter. In principle, the main difference between an insulator and a conductive spherical shell is not the force upon the internal particle when it is in the center, because in Weber's case, it will be the same in both situations. But when the test particle is not in the center any longer, according to classical electrodynamics, Lorentz Force law, for instance, when the test particle is outside the center but still inside the shell, the force will remain zero, because the electric field will be zero, no matter which point inside the insulating charged spherical shell. But when we have a charged or not spherical shell, when the test particle is away from the center, then there will be induced image charges upon the surface of the surrounding shell. And these image charges will create a net force upon the internal test body, attracting it towards the wall, the surrounding. And these electrostatic effects may mask or may complicate the analysis of the experiment, or the orders of magnitude can be even greater than the Weberian mass, and so on, because these electrostatic effects are always great. So the ideal situation when I published my paper in '93, I did mention explicitly in the paper that the experiment should be done with an insulating spherical shell, if possible.
Okay. Very good. I think this question is also for you, Andre. Did you compare the work of Oleg Jefmenko with your work? I believe that's for you. This is from Theory de Mies.
Jefmenko. Yes. Yes, Jefmenko has some works along this. It's not exactly classical electrodynamics, but it is not Weber's electrodynamics as well. But his approach is also similar to Lorentz Force law, because also in Jefmenko's work, there is a component of the magnetic component of the force depends upon the velocity of the charge, either relative to the observer or relative to the frame of reference. And this is completely different from Weber's formulation. To me, this is a very clear, even philosophical point. To me, the test buddy is interacting with other test buddies. So, like in Newton's law of gravitation, which depends only upon the distance between the interacting masses, not between the distance between a satellite of Jupiter and myself. The force upon a satellite of Jupiter depending upon the distance between the satellite of Jupiter and Jupiter. So to me, the same should happen even when there are velocity and acceleration components in the force law. So the force should depend upon the relative velocities and relative acceleration between the interacting bodies, not the relative acceleration between a test buddy and myself, or between the test buddy and a frame of reference. So this was the main reason why I did begin to work with Weber's law in the first place when I found it in the history of science books.
Okay, I think there's another question or comment at least. This one is says, oh, when you have acceleration in your formula, you should also include radiation reaction. It seems that this is neglected. Could you comment on that?
Yes, this component is not there in Weber's law. As I said, Weber's is not based on field concepts. There are some people, for instance, the late Paul Wesley did extend Weber's formulation to include the field concept. Also, Domina Spencer in the University of Connecticut is doing some works along these lines. But I myself didn't work with these formulations. But there are people introducing the retarded time into Weber's electrodynamics in order to deal with these effects. You see, Weber's formulation was the main formulation of electrodynamics at the end of 19th century, but it was completely forgotten during the whole 20th century. Only recently has it been brought back to life. So everything needs to be done. So I invite all of you to make experiments, to make calculations, to make readings, new ideas, because this paradigm, everything about solid state physics.
Okay, good morning. My question, I've known a lot about Weber's force and A couple of compliments. First, I found that in the past it's been very difficult to find any papers by Weber, and hopefully you're working to solve that rather difficult problem. My question goes to the nature of magnetism in Weber's theory. Is magnetism something that's real? Is it a real field? Or what is the role of magnetism? Does it not exist because it's merely something produced by charges in motion, or is it a real field, or not? Could you may not understand what I mean, but could you tell us a little bit about that? Because, okay, good. Well, that's exactly what I thought.
Yes, yes.
Well, thank you very much. Very interesting discussion this morning. No, I could make a lot of comments, but they're probably not really based on any real understanding. Appreciate the. I would have liked a little more detail on the experiments that you discussed, but that's just a comment on my part, because I'm sure that a lot of the listeners really want to know just exactly how this was done and all of the details and everything, and so that sort of left me wondering. But I guess the way to really deal with that is to try to read the papers and see how they were really done, and then you can ask questions.
Newtonian, talking about interaction, direct interaction between entities of the same nature. Weber was heavily influenced by the work of Ampere, and even his planetary model of the atom is a development of the Amperian microscopic or molecular currents. When Weber, he was convinced, initially he was in doubt about the existence of these molecular or microscopic currents, but later on he was convinced they were there. And then he did, instead of thinking about rings of charges, continuous rings, he did concentrate these charges into particles. And so the origin of his planetary model of the atom was that instead of like a ring of Saturn, he did have a moon, a planet, planets orbiting around the sun, or the moons orbiting around the planets. So magnetism to Weber was essentially due to interaction of charges in motion, not due to fields.
Okay, he's there. Go ahead.
Okay, great.
Any more comments, Harry?
Yes. Yes. Okay. Okay. I can see some questions here. Maybe I could try to answer them, David.
Absolutely, go ahead.
Okay. There is a question here by Jerry Hines Sec. If you do not have fields, then charged capacitor does not store any energy. How do you explain that? Well, that is the usual explanation given in Coulomb's force, that the energy will be the energy of interaction between the, for instance, either the negative plate of the capacitor and the positive plate, or if you have a test charge inside the capacitor, there will be the interaction energy, the Coulombian interaction energy Q1, Q2 over R. You don't need to talk about fields. You have interaction energy, potential energy between the interacting charges. I also see here a question by Baunis. Is this model an action at a distance model? Considers or not advanced retarded potentials? Well, I will answer the two parts of this question. Yes, Weber's model is an action at a distance model. Also, Weber himself did believe in an ether, as was typical of almost all physicists in the 19th century. His electrodynamics is expressed in a action at a distance force law. And but as I said here, Weber was the first to derive the equation of signals propagating at light velocity, as I'm putting here once again this slide. This was obtained by Weber and Kirchhoff in 1857, before Maxwell. And they were both working with Weber's electrodynamics. So although it is an action at a distance formulation, when you have many body interactions, there will be a collective signal, a collective behavior of this system which moves along at light velocity. The first time in the history of physics in which this telegraphy equation was obtained was by Weber and Kirchhoff, before Maxwell. And Weber had also introduced this constant C in 1846 for the first time. And he was also the first to measure this quantity for the first time, together with Kohlrausch in 1855 and 56. And he did publish these results. Everything which I'm showing here was known by Maxwell when he did introduce the displacement current later on. As regards the, so this is part of the answer. The second part is that also it is an action at a distance formulation. As I said, there are people trying to express Weber's formulation in terms of the field concepts, or introducing time retardation into Weber's electrodynamics. So these are some new developments, which I will not go into details here, but I quote some of these authors like Wesley, Paul Wesley, Domina Spencer, and a few others in my books and papers. As regards the advanced retarded potentials, once again, no. It is a pure action at a distance formulation by Weber. But as I said, he did believe in an ether. And his ether was composed of, it was not a continuum, it was like a gas, but a gas of positive and negative charges. So even of dipoles oscillating or vibrating. or rotating around one another.
Okay, we have some more questions. Here's one. Has Andre got a physical mechanism which can explain the value of the speed of light?
No, I have no physical mechanism for this. I just want to point out once again that Weber was the first to measure that purely electromagnetic magnitude C, which he did introduce in order to connect the force of Coulomb and the force of Ampere. So they are different magnitudes, and he did need an electromagnetic constant relating these two magnitudes. And he did perform an experiment, had no idea whatsoever of the order of magnitude of this constant back in 1846. And when he did perform the experiment, for everybody's surprise, I guess, they did find light velocity in vacuum. And then just afterwards, Kirchhoff and another student of Weber, Riemann, in Göttingen, they were expressing propagation of potentials with this Weberian constant C. So they did show the connection with optics, but I don't know any reason why it should be 3 times 10 to the 8th power meters per second and not other numerical values. I don't know why.
Okay. Again, we have it open for any questions. One of the comments was references to Weber's nuclear model. I did add Weber to the database just now, and I noticed that Andre does have some links of some translated works, which I'm going to start putting up there in our database to make it easily accessible. So I guess you're mentioning the nuclear model by Weber. Have you compared some of Weber's nuclear models to some of the more modern nuclear models like Bill Lucas and others, like the toroid models?
No, no, not yet. As I said, this is an open topic. The work which I did develop with Herr Wiederkehr last year in Germany, we hope to publish it in English in the near future. It will be called Weber's Planetary Model of the Atom. So in the near future, we hope to publish it in English.
Very good, very good.
I call attention once more that also Weber's original paper of 1846, in which he did present for the first time his force law, has already been totally translated to English as well, and is available in PDF format in our homepage. Not only the planetary model, but also the original paper of 1846.
I just added that to the database. So we got Weber in there with a nice picture from, I'm stealing this all from your website, but I think this is a great way one of the great things about this database is allows us to, yes, and so you've done amazing work. And I think one of the great things I see a lot are when people study relatively unknown scientists that did amazing work that just didn't get the publicity. To see the scientists today going back and getting those works, preserving those works, translating those works, that's just a great goal for us to have, to create these documents that it's hard. If you don't read a certain language, you can't get to it. I know Greg Volk has worked a lot on this and continues to work. It's a great endeavor, not only the science itself, but yes, go ahead.
And I opened I had always a great interest in the history of physics, but during my student days I didn't know German, and I wanted to read Weber's original works but could not. Nowadays, after my stays in Germany, I can read and speak in German, and I am opening here for those of you, especially the German scientists who are interested in Weber's electrodynamics. If you could help me, I would like to participate in this English translation of his other major electrodynamic memoirs, publications. Of his 8 major memoirs, only 3 have been translated into English up to now. But in the slide which I'm presenting here now, it's once more the main distinction between Weber and Lorentz. So once more I emphasize to all of you to try to repeat this calculation. The force exerted by a uniformly charged spherical shell, which is at rest, acting upon an internal electron, which is accelerated relative to the shell. And we can do the calculations very easily when the test body is passing through the center of the shell and is moving along the z-axis. And you will see that there will be 0 force according to Lorentz and a force different from 0 according to Weber. Try to repeat these calculations, and then you will see the whole difference between these two formulations.
Excellent. See if we have any more questions here. Some discussions going on. One of the things that actually mentioned by Greg Volk was the difference he's calling relational physics, I believe. Yes, instead of relativistic. Do I have that right, Greg and everybody? Talking between the relativistic versus relational. Can you, for those people who are not so versed, myself, I'm hanging around a lot of electrical engineers, but can you talk a little bit about that concept? I think that's fascinating. In fact, Greg, I think that's something we should look into, is almost forming a group, because one of the things I certainly am trying to get away with, I know a lot of people, I know Harry's here, they're talking about relativity, but I'm not a fan of the idea that relativity should stay around at all, but maybe the idea is we should talk about things relational instead of relativistic. Maybe that's our way of getting out of all these talks and worrying about, twins and all those kinds of things, which just really get us using a lot of energy going, I think, sideways. Can you talk about, is this something maybe we need to talk about more, or this idea of relational versus relativistic? Maybe just throw away relativistic and really just talk about relational?
Okay. Yes, that's an excellent point. My main fight is against Einstein's special and general theories of relativity. Why? In the first place, because this name, also it appears relative, relativity, it has more absolute magnitudes than Newtonian mechanics, because we also have light velocity as an absolute quantity, and these to me are very, they do not comply with my physical intuition. So I prefer the word relational, and the meaning is what I'm presenting in this slide here, that it depends only on the distance between the interacting bodies and the time variations of this distance between the interacting bodies. In Lorentz Force, which with the Einsteinian, with the interpretation of Einstein, the velocity which appears in Lorentz Force is the velocity of the charge relative to the frame of reference. So this is a very strange situation, and I am totally opposed to this formulation. For this reason, we did write the book on relational mechanics, which goes totally against Einstein's special and general theories of relativity. This book, which we are presenting now in this slide, which we did publish by Ampere in Montreal, the main topic is Newton's bucket experiment, which Newton did develop, perform this experiment, trying to show the existence of absolute empty free space and its influence upon accelerated bodies. With relational mechanics, which is based on Weber's law applied to gravitation, we implement mathematically the ideas of the Austrian physicist and philosopher Ernst Mach, according to which it doesn't matter if we rotate the bucket relative to the ground, or if we let the bucket stationary and spin the whole universe in the opposite direction relative to the ground, then according to Mach, the curvature of the water should be the same. And this does not happen with Einstein's general theory of relativity, but it does happen mathematically according to relational mechanics. So in this book we have a whole chapter, chapter 6, where we show the reason why we are totally against Einstein's special and general theories of relativity. We cannot have both of them together, relational mechanics and Einstein theory. At least one of them must be wrong. So we propose experiments to distinguish them. So thanks for pointing this out, David.
Okay, that was one of the other things. You know, Greg and I have been working with a group of people, and we're looking at hopefully getting people in funding for doing some serious funding to do some experiments. So one of the things you may want to do is, I don't know if Greg's already been talking with you, but we're looking to collect in the next year or so, you know, experiments that really could be done, and these kinds of experiments you're talking about, I think would qualify. So I don't know if you've talked with Greg, or I think we will be talking to you about that. But we have any more questions or comments? Let's see. Yeah. Okay.
Okay.
I think we're okay. We're coming up to 9 o'clock here in the morning. That's almost 2 hours. If we have anybody who wants to make any more comments, here's one. Professor Assis, isn't relational mechanics similar to Newton's fixed time assumption? This was changed when Einstein discussed that time changes. From Robert Kemp.
Not exactly, but this topic still needs to be discussed in more details. So, but it's not completely similar with Newtonian absolute time, and also it's not similar to the Einstein's concept of time in his theories of relativity. Relational mechanics is based on relative time, on the ideas of Leibniz and Ernst Mach, but we need to discuss that in more details in another opportunity.
Okay, we have another question. How is distance and time defined in this presentation?
Sorry?
It says, a question from Bones. How is distance and time defined in this presentation?
Okay, I know. In relational mechanics, I say that the distance between two bodies is a primitive concept. I don't know how to define it. And also the time between physical events. To me, these are primitive concepts that we need in order to talk about other more complex concepts like force, equation of motion, orbits, and so on. But to me, distance between two bodies and time between two events is a primitive concept.
Okay, one of the things I would ask Andre is maybe one of the really nice things about the database, I think probably one of the most interesting, if not most interesting other than the content, is the assumptions and definitions. So I would encourage you to go to our database and fill out some of your assumptions and definitions. That helps everyone understand that I think a lot of these questions come from, we're trying to get those, as you say, they're just fundamental things. Eventually, as Greg says, you have to assume something. You can't, have a definition for everything. It's impossible because every time you have something, there has to be a definition of that. And so it's an infinitely impossible task. So, but what we do say is that you have to sort of start out with certain basis assumptions and definitions. So I think it would be great to have you try to define some of those that you're working with in our website, and then what that allows people to do is on our website, then those people who define even terms, those same terms, so you can look through the whole database and see how different people define those things. So it's I think that would be wonderful if we could get some of that from you on that. Let's see, any more questions? I guess Bone's asking how are they measured.
Okay.
Any more questions from anybody before we end this session? We are recording. This will be available usually within about the next hour. So if you came in late and did not see part of Andre's talk, you'll be able to see that. And we are moving these. I am now copying these to our own server, so we don't have the problem of some of the older links disappearing. So we're working on that. DimDim is moving their servers and claims they will have those back and working if they are not working. Well, I guess there's a comment. This is a fundamental question. It's not enough to measure relative distances because they're relative, but forces based upon the distance squared will be different. A comment from Mike. I'm not sure if there's anything you'd want to say there, but if not, then what we'll do is we'll ask Andre Assis to make some closing comments before we close this recording, and thank him once again for coming by and everyone else. And as Greg said, we're very happy to have some of the great minds here today, and some of the regular people here are also great minds to be here with the presentation, and we thank Andre for taking the time. So Andre, if you could make some closing comments before we stop the recording, that would be wonderful. Go ahead.
Okay. Thank you very much once more, David, Greg, and all of you who did watch me today. I am at your disposal for to exchange ideas by email and so on. And I hope you will join me in this effort to bring Weber's work back to life, either experimentally or theoretically. So thank you for your attention.
All right, thank you, Andre, and thank you very much for bringing this up. I think, again, it's an incredible thing to see so many people who are not only great scientists of our time and alive now working, but to really bring to the forefront others that have gone before that maybe we neglected or didn't see. I see that in a lot of people's work, and I think that's just as commendable, and I very much encourage everyone to help out in that situation. We do have our database. I think what's great about the database is it allows us to log without any, how do you say, harassment on subject. We can log what we consider to be great science, and we added Weber today to our database, and we hope to keep growing that. And again, thank you very much, Andre. We're going to be stopping this recording, and again, it'll be available very shortly. Thanks so much.